Hi everyone, welcome to our lesson on stopping distance. This is part of the forces, movement, shape and momentum topic. Let's start with the specifications. So the specifications are the same regardless of whether you are studying for dual award or physics separate. We'll be looking today at knowing that the stopping distance of a vehicle is made up of the sum of the thinking distance and the braking distance. We will also be looking at describing the factors affecting vehicle stopping distance, including speed, mass, road condition, and reaction time. So let's get started by recapping a bit on forces. So we already know that forces are vector quantities, and a vector is simply something that has a magnitude and a direction, so a size and a direction. And forces are examples of vector quantities by opposition to scalar. Forces are measured in Newton, and we abbreviate that with a capital N because it's named after someone. It's named after Isaac Newton. Forces can cause a change in motion, so the speed or the direction of an object, or both, or the shape, such as bending, stretching, compressing, etc. And the force always results from an interaction between two or more objects. Now, the object don't need to be touching necessarily, so it could be non-contact, but there are always two objects interacting with each other. So let's have a look, first of all, at the importance of physics with regard to vehicles. Physics is crucial in the engineering and running of cars, but also all other vehicles such as bikes, planes, etc. But physics is very, very important, and it's very important in engineering. For example, Newton's second law, which we would have seen in another lesson, helps people design cars that can accelerate faster. And the way they do this is they keep the mass of the car low and the driving force from the engine high. So if you look at racing cars, for example, they are usually very, very low. They're also very close to the ground. And once again, this is due to physics and the center of mass of the car. But physics is incredibly important to design cars that are efficient. The cars also have brakes, and the brakes will allow the car to slow down or decelerate as and when needed. And there will be more of these in the momentum lesson for people studying for separate and for physics. So brakes are very important because they allow the car to be able to be driven safely and slow down and decelerate as necessary. They're also designed so that they can slow down not too fast so that it doesn't cause any issues to the driver and the people inside. So here we've got a car on a bus, and you can see that the car on the right-hand side, the bus, would be a lot heavier, will have a bigger mass, so it will take him longer to accelerate than the one on the left, which is a smaller car, which will be accelerating faster. And that's because of Newton's second law of motion, which states that the acceleration is directly proportional to the force, but indirectly proportional to the mass. In other words, the bigger the mass, the smaller the acceleration. So how do the brakes work? Why do the brakes matter? And this is to do with friction, the force called friction. And friction is an example of a contact force. If you remember, I mentioned that forces usually are always dependent on two objects acting on one another. And some forces don't require the object to be touching, such as gravity, magnetism, and these are non-contact force. But friction requires the objects to be in contact with each other. We said that friction is a contact force because the object must be in contact with each other. The brakes will increase the friction between the wheels and the brake pads so that it is important to maintain vehicles in good condition to keep them safe. In order for friction to actually slow down the vehicle and to absorb some of that energy, they need to be in very good condition. And you've got here two pictures. On the left-hand side, you've got brake pads from a car and they are being checked. These are checked regularly to ensure that they don't get worn off because friction will impact the brakes because they get worn off because of the friction between the wheel and the brake pad. So they need to be checked regularly and they need to be replaced sometimes. On the right-hand side, this is a side view of the brakes on the wheel of a bicycle. So the bit at the bottom are where the little pads are, and that's what will be applying pressure on the wheels of your bike and allowing the friction to slow down your bike. Now, tires will have a thread or grooves, and these are designed to help friction between the tires and the road surface. So you've got here a picture of a tire for a car, and you can see the grooves very clearly. And there is actually a legal limit below which the grooves are no longer deep enough for the tire to be safe, and the tires need to be replaced. Bikes will also have grooves, and depending on where you want to use your bike, then you might have slightly different tires with slightly different grooves. In particular, if you want a mountain bike, you will need thicker grooves to be able to adapt to the different surfaces you're going to be riding your bike on. Now, those grooves are very useful because the water that might be on the road can travel inside the grooves while the rest of the wheel can stay in contact with the road, therefore ensuring that we've got friction between the road and the tire, even when the road is wet. The friction will act in the opposite direction of the vehicle's motion. So if the vehicle is moving forward, the friction will be moving back. And what the friction does, it will convert the kinetic energy and slow down the car. So if you remember, kinetic energy is the energy of moving object, which you will have seen in Key Stage 3. You might not have seen the topic yet on how to calculate kinetic energy, but kinetic energy is linked to the mass of the vehicle as well as its speed, its velocity. And what the friction does is it will convert that kinetic energy, that speed, into other type of energy such as heat that will be dissipated to the environment, and therefore the speed of the vehicle will reduce and it will slow you down or allow you to come to rest. So how does it all work together? The road, the brakes, tire condition, all the things we have mentioned. Well, if the brakes are worn out, which I've mentioned before, need to be checked regularly, there will be less friction. The grooves will be smaller, there will be less friction between the tire and the road. And that will make deceleration more difficult. It will make that absorption of that transfer of kinetic energy harder. And therefore, it will take you longer to slow down and to come to a stop, which obviously is dangerous if you are braking to avoid an obstacle, for example. Similarly, if the tires are worn out and the grooves are no longer deep enough, there will be less friction, which will make deceleration more difficult. And that's because the water, for example, might not be able to go through the grooves and therefore will create a little barrier between the tire and the road. And that's going to be making it harder for you to decelerate, to reduce the friction, and potentially be dangerous. Now, the road condition can also impact the ability of a car to slow down and come to a stop safely. So we know that the brakes will impact the deceleration because if they are worn out, there'll be less friction. The tire will impact the ability of a car to slow down because if they are worn out, it will reduce the friction and make it harder to stop. But the road condition can also impact the ability of a car to slow down. For example, wet, snow, icy road can all reduce friction. And what that might mean is that the car ends up sliding. And sliding is when you are losing control of the vehicle because there is less friction, so you cannot control the direction of your vehicle as much. When this happens, the driver loses control and it makes it very difficult to steer in the direction wanted, and that is very dangerous. So wet and icy road will usually require people to drive more slowly so that they are able to reduce their speed from a lower speed. So it's not as dangerous as if you are driving very, very fast. And actually in France, there are different speed limits depending on whether it's raining or not. And when it's raining on the motorway, there is a lower speed limit to account for the fact that it would take you longer to slow down and to stop. So it is a distance, the braking distance is a distance the car travels between the moment the brakes are applied and the car coming to the stop. That's a definition of braking distance. Now be very careful. You need to include the word distance in your answer. The braking distance is not a braking time, it's a braking distance. So it's a distance the car travels between the moment the brakes are applied and the car coming to a stop. Okay, so imagine you start, you press your pad, you press your pedal, your braking pedal, or you apply the brakes on your bike, then you can almost like start a timer, and the distance you're going to travel between that moment and the moment your vehicle stop, that is your braking distance. Just to sum up, it is affected by the speed of the car, the mass of the car, the road condition, and the car condition, in particular its brakes and tires. Obviously, I say car, but it can be any vehicle, such as a bike. Okay, but that's what you need to know. Why is it affected by the speed? Well, the faster you go, the more you're going to have to reduce, the more deceleration you're going to need, because deceleration is changing speed over time. The mass of the car, we also saw that because of Newton's law of motion and F equal ma, you're going to need a bigger force to be able to stop the car. Road condition, we've mentioned icy, wet, snowy condition will reduce the friction and therefore increase your braking distance. And finally, we've mentioned as well brakes and tires. If they are not working properly, they will also increase your braking distance by reducing the friction. So let's have a look at something else that we need to take into account when we are trying to get our vehicle to come to a stop. And this is a thinking distance. And the thinking distance is different from the braking distance. Another thing to take into account when we're looking at cars and the car trying to slow down or come to a rest is the thinking distance. And the thinking distance is different from the braking distance. So the thinking distance is a distance the car travels between the driver seeing an obstacle, for example, a red stop or deciding to stop, and applying the brake. So it takes a while, obviously, between you registering that there is an obstacle or that you need to brake, or red stop, for example, and you actually pressing the brake. And that's the thinking distance, is a distance you're traveling while you are thinking about stopping the car, basically. It's affected by the thinking time. And if you are studying for biology, you might have done some work on thinking time and reaction time. It can be calculated by the distance will be equal to the speed the car is traveling at and the time it takes for the driver to apply the brake, as the car will usually be traveling at a fairly constant speed. The thinking distance can be affected by tiredness, distractions in the car, alcohol, drugs, medication. So there are factors that will affect how long the thinking distance is, okay? How long the thinking time is, and therefore how far we are traveling while thinking about applying the brakes. So let's look into more details at these factors. Tiredness will increase your thinking time. Because you're tired, your brain will not be quite as quick at registering the obstacle and then giving the signal to your muscles to actually apply the brake. And because it will increase your thinking time, it will increase your thinking distance, because thinking distance is speed time time. So if the time increases, then the distance will increase. Older people will also often have a longer thinking time. They're not as quick at responding to signals. So our older people will tend to have a slightly longer thinking time, which therefore will result in them having a further thinking distance. Distractions, so for example, using a mobile phone in particular, is of a great concern when people are driving, because it distracts you from the road, it distracts you from what's happening on the road. Your brain is busy looking at your mobile phone, maybe messages or changing your track or whatever it is you're looking at on your phone. Your brain will be busy doing that rather than looking at the road, and therefore it will take you longer to react to a signal on the road. As a result, it will increase your thinking time and therefore increase your thinking distance. Other distractions include children in the car, for example. Children might be arguing, they might be making noise, they might be just talking to you, and that will once again require some of your brain power. And while you are looking after your children or you are trying to respond to whatever signal they're giving you, then it will take some of your brain power, and once again, it will increase your thinking time. Because it increases your thinking time, it will increase your thinking distance. If you've got pets in the car and they're moving around in the vehicle, once again, you might be busy looking as to what they're doing, making sure they're safe. And once again, it will increase your thinking time and therefore increase your thinking distance. Loud music might also affect your thinking time, or especially if you're busy singing along or focusing on that instead of on the road, then once again, might increase your thinking time. Because speed equals distance times time, it will increase your distance equals speed times time, then it will also increase your thinking distance. Distraction makes it harder to pay attention to the road and to react quickly, and it increases thinking time and therefore the thinking distance. Alcohol, so there is a legal limit within which you're still allowed to drive on the road, even if you've had a drink, as long as you're within the legal limit of alcohol in your blood. But even if you are within that legal limit, alcohol will have an impact on your reaction time. Alcohol will typically slow down your reaction time, and therefore it will increase your thinking time and increase your thinking distance. Now, I always tell my students that if on top of it, even if you have only had a drink, you're well within the legal limit of alcohol in your blood, imagine if you're just slightly slow at reacting, and on the other side of the road, the person in the car opposite has also drunk a bit, is also slightly slower. It will have a big impact on the likelihood of having an accident. So my advice would always be, if you've had a drink, personally, I wouldn't jump in a car at all, even if I think I am within the legal limit of alcohol in my blood, just because I know it will affect my thinking time, therefore it will increase my thinking distance. It's important to notice that many people who are killed on the road have been drinking, but are within the legal limit. So just being within the legal limit doesn't mean that you are necessarily as responsive to what's happening on the road. Therefore, it's something to take into account when you go behind the wheel. Drugs usually have the same effect as alcohol. So once again, it will increase your thinking time, therefore it will increase your thinking distance. Now, some medicine you might be prescribed, might also affect your thinking time and therefore your thinking distance. Some medicine might make you drowsy, which means when you're a bit sleepy, you're a bit slower at reacting to things, which will make you slower to reacting to things on the road as well, increasing your reaction time and therefore your thinking distance. Now, it's important when you are prescribed medicine or you are taking any medicine over the counter to read the information leaflet. And I know sometimes people think, oh, that's okay, I know what I'm taking, but I would still think it's important to read the information leaflet with any medicine you are taking. And if you have any doubts, speak to your GP and let the DVLA and your insurance know if you are taking any medicine that might affect your thinking time. Otherwise, it might impact on your insurance, for example. Now, this is taken from the DVLA website, and it is telling you that it's an offense to drive if you have over the specified limit of certain drugs in your blood and have not been prescribed them. But also, if you've been prescribed any of the following drugs, then you need to talk to your GP about whether you should be driving. So the list is amphetamine, clonazepam, diazepam, flunitrazepam, lorazepam, methadone, morphine or opiate or opioid-based drugs like codeine, tramadol or fentanyl, oxazepam, and temazepam. Like, for example, codeine is something you can get over the counter mixed with paracetamol. Now, this is not something you need to know for your GCSE, but I do think it is important that people, and especially young people, are aware of the effect of prescribed medicine or over-the-counter medicine on potentially your reaction time and therefore your thinking distance. Now, your speed affect both your thinking and braking time. The faster you go, the longer it's going to take for you to stop the car. Okay, so it is important to respect the speed limit, obviously, but also to make sure that you have enough space between you and the car in front of you, because you will still be traveling while you are trying to stop your car. And the distance you are traveling while you are trying to stop your car is significantly higher if you are driving faster than if you are driving slower. You travel further while thinking about stopping if you're driving fast, because the thinking distance is speed times time, but you also travel further while braking because more kinetic energy will need to be converted into heat and dissipated to the surrounding. So the faster you go, the longer your stopping distance, okay? These are, if you've ever had a look at the theory test for driving, this is something that is part of it, and it just gives you an idea as to how long it takes for you to bring your car to a stop, depending on the speed you are going at. So if you can see that if you are driving at 20 miles per hour, it will take you about 3 car lengths to stop. It's still significant if you think about 20 miles per hour being not very fast. 3 car length is still a very, very big distance to be traveling. Okay, so you need to be well aware of, what things are around you. On the motorway, you might be going up to 70 mile per hour, and that's 24 car length to stop. Okay, and every now and then on the motorway, you will see those areas where you've got some signs on the road that enable you to make sure that you've got enough space between you and the car ahead of you. Now you can see as well on that graph that if you double your speed, you double your thinking distance, but you do not double your braking distance. Okay. That's because the braking distance is not going to be directly proportional to your speed, because your speed will be varying while you are braking. It will be going down and down and down and down. Okay. Your braking distance increases exponentially with your speed. So let's just have a look at some practice question. This one is asking you to state the formula linking average speed, distance traveled, and time taken for 1 mark. And then the car traveled at 21 meters per second. The driver's reaction time is 0.14 seconds. Calculate the distance traveled by the car during the driver's reaction time. That's for 2 mark. So pause the video and have a go. Okay, so we know that speed equal distance over time. So you can write speed equal distance over time, or you might want to put that distance equal speed time time. Both of these would be correct. In terms of the distance traveled, you simply need to multiply the speed by the time. So 21 times 0.14 seconds. But let's have a look at the mark scheme. So speed equal distance divided by time, but it says allow any correct rearrangement. So putting distance equal speed time time would also give you the mark. Okay. In terms of your calculation, 21 times 0.14 will give you 2.9 meter. Here's another question. So that question is also linked to your lesson on Newton's laws of motion. And the question is telling you that a car experiences a braking force of 7,600 Newton. The car has a mass of 1,200 kilogram. Say the formula linking force, mass, and acceleration, and then calculate the acceleration of the car. Pause the video and have a go. Okay, so if you remember from Newton's second law of motion, F equal m times A, or force equal mass times acceleration. For any calculation, I would always say, write your equation first, do your substitution, then you're rearranging and write your answer. So F equal ma, force is 7,600 Newton, mass is 1,200 kilogram. There's no need for converting any unit. We've got the right unit, we've got Newton and kilogram. And then we need to rearrange our equation. How do we do that? Remember, you can do anything to an equation as long as you do the same thing on both sides. Here, I want A to be the subject of my equation. So I'm going to divide that side by 1,200. So that 1,200 divided by 1,201. But I need to do the same on the other side. Give me that A equals 7,600 divided by 1,200. Going to put that in my calculator. And it's going to give me an answer of 6.3 recurring. Okay, and the unit is given to you meter per second square, or meter per second per second. Let's have a look at our mark scheme. Okay, mass equal force times acceleration, and then you can see an answer of 6.3 meter per second square by doing 7,600 divided by 1,200. So in this question, you asked to calculate the braking distance traveled as the speed of the car is reduced from 21 meter per second to 0 meter per second. Now you are given the equation, okay? You are not given the equation in the question, but you are given the equation in your equation sheet. So that got copied and pasted from me from the equation sheet you are given. So you don't need to remember this equation, but you need to be able to locate it on your equation sheet. So please do spend time before your exam familiarizing yourself with the equation sheet so that you know exactly what is in there and how to use it. So pause the video and have a go. Please note that the V is for final speed, okay, which is there, final speed, and U is for initial speed, and these are square. So pause the video and have a go. Okay, so the final speed is 0. And as usual, I start with just my substitution. That's the easy bit. Now, if you remember our acceleration, we just calculated as 3.3 meters per second square, and s is the distance, okay, or unknown. So we're going to start by getting rid of that 21 square on that side. We can do this by taking away 21 square on that side, but we need to do the same on the other side. So it's going to give us minus 21 square equal 2 times 6.3 times s. Now the 6.3, the deceleration, so technically it would be negative, okay? Now we can isolate the s, put it as the subject of our equation by dividing that side by 2 times 6.3, but obviously we need to do the same on the other side. That's going to simplify itself and it's going to give us 1. And then we simply put that in our equation. So minus 21 square divided by 2 times 6.3 or minus 6.3, which is why you're going to have an answer that is negative. It's because the deceleration was negative. And then you put it in your equation, in your calculator. Make sure you put brackets when you are putting this number in your equation. Make sure you put this in brackets. Otherwise, you might not get the correct answer. And you should find an answer of 35 meters. Let's have a look at our mark scheme. Okay, so substitution, like I said, ECF means error carried forward. In other words, if you calculated the wrong acceleration, but you're using it correctly in your equation and you are substituting correctly and it's clear what you've done, then you will not get penalized for using the wrong acceleration, as long as the one you've calculated in the answer before. And then you can see the distance calculating at 35 meters. Okay, I just wanted to put there a couple of graphs that links to our velocity time graph. So here you can see a comparison between two braking distance graph for two cars braking at different rates. Now they are starting from the same velocity, as you can see. And remember, the distance for a velocity time graph is the area under the graph. So that would be the area here will be your braking distance. Okay, that's the braking distance. And you can see the one on the left, as the accelerator is faster, it has got applied a bigger braking force, and therefore it stopped into a shorter time than this one, which has decelerated at a smaller rate. Therefore, this one has covered a shorter braking distance than this one. Now, we can also compare two cars that are starting from two different speeds. Okay, you can see here the one on the left has started from a higher velocity than the one on the right, and therefore it took it a longer distance to come to a stop. That's assuming they've got the same braking force. And once again, if you look back at the area under the graph, which is our braking distance, you can see the braking distance for the one that started at a higher velocity will be bigger than the one for a car that was traveling more slowly, even if the braking rate is the same. Okay. So this is it for me today. If you want to read some notes about this from your textbook, please have a look at pages 31 to 33. Have a go at the questions on there. Rewatch the video if need be, and please do have a go at the questions. That's it for now. I'll see you again very soon. Goodbye.